Um, it tells you this thing is speeding up because there's torque on it, so you can draw energy bar charts for this. At time 0, there's no energy in the system, it's not moving. And then at 22 seconds, it is moving, it has rotational kinetic energy. So that means there must be energy flowing into it, there must be work done to it, and the torque is doing work to it. Okay. Calculate the angular acceleration of each particle. All right, well, that's going to be through kinematics. You know the initial speed is 0, the final speed is 6, the time is 22, and so I would use Vf equals Vi plus At to find the acceleration. Calculate the angular displacement. So that's going to be some more kinematics. You know the initial speed, you know the final speed, you know the time. So you could do d equals v bar t and solve for the distance, the angular distance in radians. Calculate the amount of working done. Okay, so there's a couple different ways you could do this part. You could say, we know the work is equal to force times distance. Well, work is also equal to a net torque times the angular distance, and you just found the angular distance here. And let's see, we don't know torque, do we? Well, we know that torque is equal to I alpha. You found alpha here, they give you I, so you can do I alpha, and then so I 143 times the alpha times the angular displacement, and that should give you your answer. Another way to do it, though, is to realize that the working must be equal to the change in rotational kinetic energy. Well, that's going to be equal to 1/2 I omega final squared. So 1/2 of the I they give you times that right there squared. And it should give you the same answer. You should do both of them. Make sure it does. Okay. Another thing you should do is they give you I, but you should be able to figure out I for yourself too, because they tell you the mass of all these things. And it's spinning, let's see, which way is it spinning again? About the z-axis. So it's spinning like this. So we need to really know what this distance is here. Well, if this is 6, and this is 4, so that means this is 3, and this is 2. So you should be able to find that distance there. That's going to be square root of 2 squared plus 3 squared. And that's going to be the same distance for all of them. So you can do mr squared. Well, that's nice, since it's really going to be, okay, so it's going to be 3 kilograms times the quantity 3 squared plus 2 squared, and then add to that 2 times the quantity 3 squared plus 2 squared, and add to that 4 times the quantity 3 squared plus 2 squared, plus the 2 times the quantity 3 squared plus 2 squared. Anyway, you should get 143. You should check that too, just to make sure. Okay. Okay, so it starts at rest and it's going to be speeding up. It accelerates at that rate, and we're supposed to do energy bar charts again. So there's no energy at first. At 100 rads, there would be rotational kinetic energy. That means the system gained energy through working. Okay. Calculate the angular speed of each particle at at 100 rads. Okay, well, I think I would use Vf squared equals Vi squared plus 2AD, because you're trying to find the final angular speed. You know the initial 0, you know the acceleration, and you know the displacement. So you should be able to figure out what the final angular speed would be. Notice it doesn't say linear speed, it says angular, so that should be good. Then calculate the amount of working done from 0 to 100. Okay, let's see. Well, one way is the working would be equal to the change in kinetic energy, which would be the initial is 0, so it's just simply going to be 1/2 I omega final squared, and we found the final here. So it tells you what the rotational inertia is, and we know that, so that should be pretty easy to find working. I'm also wondering if we could figure it out from working equals the net torque times the angular distance. The net torque would be I alpha. See, we found, or actually we know the angular acceleration, and we know I, and we know it's 100, so I think this one would have been easier this time. That's interesting. All right, okay. All right, so this is another way you can have an alternative fueled vehicle. Instead of having batteries or anything else, we have this flywheel. It's just something that has lots and lots of mass that's spinning really fast. And it's storing rotational energy that can be siphoned off and converted into a linear energy. Okay, so at the beginning it has lots of rotational energy. And at the end, I guess it would have lots of dissipative energy. Okay, so this is probably how fast it's spinning at the very beginning, and I'm assuming at the end it's basically come to a stop. Okay, so first of all, we have to put this in radians per second. So 4,000 revolutions per minute, and we have to do some factor label here. So in 1 rev, there are 2 pi radians, and in 1 minute, there are 60 seconds. So this will give us the angular speed in radians per second, which is what we need it to be in. And realize that the working here is going to be the same as the change in rotational kinetic energy. So the working is going to be equal to 1/2 I, they tell us, times that omega that we're going to find squared. Okay, so once I know what this energy is, okay, and it's giving me the power, and be careful here because it says horsepower, so I have to convert that horsepower into watts. But once I do that, I can use power equal to work over time. So I'll know what the power is, it has to be in watts. I know what the work is. This is omega, by the way. I don't want you to get confused. That's omega. I'll know what the work is, and so then I can solve for the time. This is just kinematics. You need to change that into meters per second. You'll know what the time is. Assume that it goes at a constant speed. You know the time, so you can figure out what the distance is. Okay, so making bar charts up here and here. The reason why this is kind of important to do it this time, especially, is because sometimes students forget about the kinds of storages of energy there. Up here, just gravitational. But here, it has more than one type of storage. It actually has 3 types of storage. It has gravitational, it has translational kinetic energy, and it has rotational kinetic energy. So there's 3 types of storages there. Okay, so it says it just barely makes it around. So let's draw a force diagram then. So if it just barely makes it around, that means the weight must be equal to the net force, which would be mv squared over r, where the weight is mg. So that means the speed right there must be equal to the square root of RG. That's what the speed must be at that point right there. Okay, so there's two parts of this. We're doing the first part. So at the top, it has gravitational energy. Here, it also has gravitational energy equal to mg2r, and it has kinetic energy, 1/2 mv squared, where that's v. So therefore, Rg, sorry about that, Rg. And then plus 1/2 the rotational inertia they give you times omega. Well, remember that omega is equal to, I'm going to make this a big R here so we don't confuse it, is equal to V over R. So it's going to be square root of Rg, this R, divided by the R of the actual ball here. Be careful because that says centimeters. So I'm going to use a little r for that, squared. So we know the mass, we know g, we know the radius of the loop, I think, somewhere. Yes, it has to be in meters, by the way. We know I is. And so that means you can solve for h. Now, the second part of this, what if there was no friction? Well, if there's no friction, there is no rolling. If there's no rolling, then it's just simply going to be Eg at the top equals Eg at the top of the loop plus 1/2 mv squared. Okay, so you should be able to go ahead and solve it then.